so good afternoon, everyone. Okay, so now we're beginning the next session on observations and diagnostics. So first of all, I'd like to acknowledge Nancy Nichols, who was part of the scientific committee for the symposium and kind of chose the talks for this session. But unfortunately, she couldn't be here this week, so instead she's asked me to chair the session instead. So as well as chairing the session, she also invited me to give the first talk of today. So my name's Alison Fowler from the University of Reading, and I'm going to be talking about some of the implications of accounting for spatial observation error correlations on network design. And this is work that's been done with also with Joe Waller and Sarah Dance at the University of Reading and David Simon at their Met Office. Yep. Yeah, can I do that? Okay. So the motivation. So as you're mostly aware, numerical weather prediction systems have been moving towards higher resolutions in order to try and capture small-scale but destructive weather phenomenon. So an example is the system that's being developed here at RIKEN, the rapid updating forecasting system. So in order to constrain these high-resolution models, we also need high-resolution observations. And yeah, so via data assimilation. But the problem is that many of these observation types have significant error correlations. And this has typically restricted the use of very dense observations that can resolve the same scales of the model within the data assimilation. But more recently, there has been advancements in terms of explicitly representing and using a non-diagonal observation error covariance matrix within data assimilation. So in order to use a full R matrix within data assimilation, first of all, you need to estimate it. So there's been quite a few different ideas for how to estimate a full R covariance matrix, including all the contributions from representativity and forward modeling errors. And this is kind of a non-exhaustive list of some of the recent work. But the methods that have proven to be really popular have been based on the de Rosier et al. 2001 method, where essentially you estimate your R covariance matrix as the covariance between the difference between your observations and your background or prior, and the difference between your observations and your analysis. And if you assume that all the data is unbiased and Gaussian, then you see what you're actually estimating in this case is the true R covariance matrix multiplied by these two terms, where we have the ratio of the true error covariance matrices, so the true R and the true B matrix representing the prior errors, and then the ratio of the assumed covariances that we're using within the assimilation. So this is only going to equal the true R if these two are equal. But part of the idea is that you should be using this, or you could be using this iteratively, and then you see that you should converge to the true R matrix if your B is correct, which is also rarely true. But despite this, the de Rosier et al. Method has proven to be really useful in terms of analysis error and forecast error, particularly for inter-channel error correlations. So these are two examples where the de Rosier method's been used to estimate spatial correlations, so for the Doppler radial winds and for AMVs, both within the UKV system. So we're estimating 20 kilometers and 160 kilometers for the two different observation types. So this kind of information could be used to improve the thinning distance of our observations, or it could be used to explicitly account for the observation error correlations. So trials have been performed at the Met Office in the UKV system using this estimate of the covariances for the Doppler radial winds. So the question is that if the density of the observations is no longer restricted by the error correlation length scales, then what density of observations makes sense? And in the case when we're advocating using much denser observations than are currently being used, how is this sensitive to the accuracy of the R that we're estimating? So to answer the first question, first we can look at optimal thinning in an optimal data assimilation system. So it's known that observations with spatial error correlation length scales have more information about small scales than observations with uncorrelated errors. But because the trace of the error covariance matrix is conserved, it means that while we're more certain at the small scales, we become less certain at the larger scales. So this implies that thinning or averaging observations with large error correlation length scales is going to remove a greater proportion of that information than observations with uncorrelated error. But obviously, the importance of the small scale information in the observations is going to depend on what's already known a priori, represented by the B matrix. So to illustrate this, I've taken a circular domain discretized into 64 grid points. And I'm taking my B and my R matrix to both have SAW correlation functions. And the length scale in my B matrix is 5. So this shows the prior uncertainty in wave space. And you see that for this function, this means that we have much larger uncertainty at the small wave numbers and much less uncertainty at the large wave numbers. And then we can look at how this measure of the information content of the observations, the degrees of freedom for signal, changes as a function of thinning distance. So the degrees of freedom for signal can be computed as the expectation of the background part of the cost function evaluated at an analysis, or it can also be thought of as a kind of the expected magnitude of a scaled analysis increment. So in the case when the length scales in our observation areas means that our matrix is effectively diagonal, we see that as we increase the thinning distance, then the information content per observation reduces with denser observations. So this is kind of a sign that there's data redundancy in having that density of observations. And this is because at the very small scales, there's more information in the prior than in the observations. And similarly, if we increase the length scales in our R matrix to 2.5, then we still get a similar shape in terms of this metric. And that's because even though we've increased the length scales, there's still less information at the small scales in the observations than in the prior. But if we start to increase the length scales in our R matrix so that they're now longer than in the B matrix, then we see that this metric now starts to increase as the density of the observations increases. And that's because now we have more small-scale information in our observations than in our prior. And so there's a benefit to having the dense observations. So in terms of this metric, it's most efficient to have dense observations when the observations have less uncertainty than the background at small scales. But in data assimilation, we're, of course, interested in the accuracy of our analysis. So we can also look at the trace of the analysis error covariance matrix as a function of thinning distance. So again, this blue line is for the case when my observations are effectively uncorrelated. And as you'd expect, as you reduce the thinning distance, so you have more observations, you get a reduction in the analysis uncertainty. And if we start to increase the length scales in our R matrix, we see that this reduction in the analysis uncertainty with increase in density of observations starts to reduce. But if we then start to increase the length scales in our observations so they're now longer than in our B matrix, then you see that the reduction in the analysis uncertainty with increase in observations starts to increase again. So in terms of reducing the trace of the analysis error covariance matrix, we see there's the greatest benefit of having dense observations when the structure in the R and the B matrix differ. So effectively, we have more directions that we can explore in terms of reducing the analysis error. So these two metrics give us a slightly different interpretation of when we'd want to use dense observations. And it's partly because this is a relative measure because we're dividing through by the B matrix, whereas this is an absolute measure. And you can show that it's more sensitive to corrections to large scales rather than small scales. So the next thing is to understand how these two metrics are sensitive to misspecifying the R matrix. So to look at this, I'm going to assume that my R and B matrices both represent errors which are isotropic, homogeneous, and a state that's directly observed. So this allows me to parameterize these two matrices. And because they become circulant matrices, and in this case they have the same dimension, then they have the same eigenvectors which are given by the discrete Fourier basis. So I can decompose both my R and my B matrix in terms of the uncertainty in the Fourier space, which also means that my analysis is independent at different wave numbers. So this means that we can produce similar diagrams to those shown in the Dorothy 2005 paper, where here I'm plotting the expected magnitude of errors projected into Fourier space. So, so this array here is the expected magnitude of my background error, which is consistent with my B matrix. This array here is the expected magnitude of my observation errors, which is consistent with the R matrix that I'm using within the assimilation. And then this full line here, including the dashed arrays, is the expected magnitude of my observation errors, which is consistent with the true R matrix. So in this case, I'm underestimating the observation uncertainties. And then the pink line is the innovation that I would expect to get, given my assumptions that I'm putting into my simulation. And the orange line is the actual innovation that I would get, given the true statistics. So in a similar way to the Dorosier paper, we can mark on what the expected analysis increment would be in the case that the assumptions are correct in the simulation. So that's this pink array. And then we can also mark on what the optimal analysis increment would be in the case when we were using the true R matrix. And then lastly, we can show what the actual analysis increment would be, given that we've got this discrepancy in the R matrix during the simulation. So the actual analysis increment will lie along the true innovation, but the weighting is done according to the assumed R matrix. So in this case, our analysis increment is much larger than the optimal analysis increment and larger than we would have assumed it would have been. And also the analysis error, given by the dashed line, the actual analysis error is larger than the optimal and larger than we would have assumed it would have been. And then we can do exactly the same for the case when we overestimate the observation uncertainty. So this time, this arrow is the magnitude of the observation errors consistent with the true R matrix, and this one is consistent with the one that we're assuming within the simulation. And in this case, the actual analysis increment is now smaller than optimal and smaller than expected. And the actual analysis error is larger than optimal, but it's smaller than we would have assumed it would have been. So in terms of whether it's better to under or overestimate the observation uncertainties, from this we can say that it's better to overestimate them, because this ensures that analysis increments are not larger than expected, so we're not overfitting to our observations. And also the analysis error uncertainty is not larger than expected, so we're not overconfident in our analysis. So this can be used as an argument for why you'd use variance inflation in the case when you're neglecting observation error correlations. But obviously we want to move away from the idea of variance inflation. And in particular, we might be more confident in our observation error variances because we have more data to try and estimate them. And we also have some information about the structure of the R matrix that we can use. So in the remainder of the talk, I'm going to focus on how these metrics I presented are sensitive to the misspecifying the length scales in the R matrix. So the first metric, which was the degrees of freedom for signal, in the optimal case is equal to this term, the expectation of the background part of the cost function evaluated with analysis, or the scaled analysis increments. And we can look at this term as the difference between the value that we'd get given all our assumptions were correct in the simulation, and the actual value we'd get given that we've got this discrepancy in our R matrix. And if you, again, assume Gaussian distributions and unbiased errors, then you see that it's equal to this, where we have the observation operator acting on the common gain matrix, so the weighting that we're given to the observations in the simulation, multiplied by this term here, where we have dt is the true covariance of the innovation, so the sum of the true R and the true B, and d is the covariance of the assumed innovation, so the assumed R and B. And if I substitute in here my circulant forms of the B and the R matrix, then you see that this can be written as a summation over the different wave numbers. So here we have the difference in the assumed uncertainty in the observations at wave number k, and the actual uncertainty in the observations at wave number k. And then this term here is just based on the assumptions that we're putting into the simulation. So the B gamma k is the uncertainty in our prior, and again we have the assumed uncertainty in our observations. So if we first look at this term here, which tells us how much weighting is going to be given to these discrepancies at the different wave numbers, then again I'm using my framework where I have this circular domain with length scales 5 in my B matrix. Then what you see is that at pretty much all scales, it's the small scales, pretty much all wave numbers in my R matrix, sorry, it's the small scales where the discrepancy in the R matrix is given the most weighting. And it's only when the R matrix tends to a diagonal that it's the large scale discrepancies that become more important. So what we see is that if then we look at this full term as a function of the assumed length scales in our R matrix, so in this case, the true length scales in my R matrix are less than in my B matrix. And then this is the case when the true length scales in my R matrix are greater than in my B matrix. And ideally, we want this term to be 0. But if it's not 0, we'd rather it be positive than negative, as that would indicate underfitting to our observations rather than overfitting. So that means that in both cases, we'd rather underestimate the length scales in our R matrix than overestimate them, which is the same as overestimating the uncertainty at the small scales in the observations. So we can do exactly the same thing for the trace of our analysis area covariance matrix. So again, looking at the difference between the value that we'd get if all our assumptions were correct in the simulation, and the value that we'd get if taking into account this discrepancy. And this time, you can show that it's equal to this. So we have, again, the k, the weighting that we're given to the observations, and then the difference between the assumed R matrix and the true R matrix. And again, if we substitute in the circulant forms for our B and our R matrix, then again, we can see that this can be written as a summation over different wave numbers, where again, we have this term here, which is the difference between the assumed observation uncertainty at wave number k and the actual uncertainty at wave number k. And then this term here, which again just depends on the assumptions that we're putting into our simulation. So if we again look at this term first, then what we see now is that the scales that are given the most weighting depends on how our assumed R matrix relates to our B matrix. So in the case when the length scales in our assumed R matrix are larger than in B, then we're given more weighting to the small scale discrepancies in our R matrix. Whereas when the assumed length scales in R are less than in B, then we're given more weighting to the large scale discrepancies in our R matrix. So again, we can see what this means in terms of the full metric for the case when my length scales in my true R matrix are less than in B, and when they're greater than in B. And again, we want this, ideally, we want this term to be 0, but if it's not 0, we would rather it be positive than negative, because then that would be underconfidence in our analysis rather than overconfidence. So this time, we see that in order to satisfy that, it means that we want our assumed length scales in our R matrix to be between those in the B matrix and those in the true R matrix. So whether it's better to under or overestimate the length scales in R depends on how B and R relate. So this is slightly different to the previous metric, where we saw it was generally better to underestimate the length scales in R. But when we do have the agreement is when we have much longer length scales in our R matrix than in our B matrix. So it's this situation when we'd actually be wanting to use the dense observations, and we have the agreement that we should be underestimating the length scales in R, so we both are underconfident in our analysis and we're not overfitting. Whereas in this case, if we might choose to use less dense observations, and so the discrepancy in our R matrix becomes less important. So to illustrate this, I'm going to use the Lorentz 96 model, where I have a circular domain discretized into 40 grid points, and I'm solving this function, this equations. And I'm simulating direct, regularly distributed observations of the state using the ensemble square root filter with 100 ensemble members, so I'm fairly confident in my ensemble representation of my prior uncertainty. So for this model, you can look at what the prior uncertainty looks like at different wave numbers. So this is for my first observation time. And we see that the blue line shows that we have most of the uncertainty in our model at the medium wave numbers, and we're more certain at the large and the small scales. And although this is obviously flow dependent, this kind of shape of the uncertainty spectrum seems to be fairly constant throughout my time series. And then in the experiments, I'm simulating my observations, assuming R follows a Saw correlation function with length scale 2. So this black line is the uncertainty in my observations. So for this optimal case, we can look at these two metrics as a function of thinning distance of my observations. And you see that this measure of information content per observation increases as I reduce the thinning distance of my observations. And that's because we are more certain in our observations at the small scales than my prior. So next, we can look at what happens when we either overestimate the length scales in our R matrix, which is the red line, or we underestimate the length scales in our R matrix, the green line. So this is what we get for these two different metrics for the case when we overestimate the length scales in R. So we see that the solid line, which you can't quite see, is the actual analysis on variances. And the red dashed line is what we assume. So in this case, we're overconfident in our analysis. And then here we see that the actual analysis increments are much larger than we assumed and optimal. So we're overfitting to our observations. And you see that this gets worse as the density of the observations increases. Whereas if we underestimate the length scales in our R matrix, then you see that we're underconfident in our observations, in our analysis. And also our analysis increments are smaller than we're expecting them to be, and also smaller than the optimal. So in the second case, we're obviously not using the observations to their full potential, but we're still able to get some of the small scale information out of the observations, and at least we're not having a detrimental impact on our analysis. And then lastly, for comparison, the case when R is diagonal. So here you see that we get the worst analysis errors, and also we're not able to use the small scale information in the observations. So just to see what this looks like for an example of the ensemble. So this is the optimal case where the black line is the truth and the black stars are the observations that I've simulated. And the red line is the ensemble mean. And then this is the case when we have overestimate the length scales in R. So it's kind of subtle, but you see that in this case we are pulling more towards the analysis. The analysis is pulling more towards the observations, and the ensemble, the spread in the ensemble is reduced compared to the optimal case. And we can also look at the situation where we underestimate the length scales in R. So here you see that we're pulling less towards the observations, and the spread in the ensemble is larger. And then lastly, this is the same example, but for when R is assumed to be diagonal. So as I say, it's kind of subtle, but if you look over a longer time series, so this is when I've averaged over 1,000 observation times, then you see that there is a marked increase in the root mean square error of the ensemble mean when we overestimate the length scales, and also this kind of problem of being overconfident and the ensemble spread being too small is obviously more marked. So to summarize, been using this metric of the degrees of freedom for signal, or the scaled analysis increments, to argue why we'd want an increase in the density of the observations when the observations are more certain at the small scales than the prior. So for example, in my idealized experiments, it's when the length scales in R are longer than in B. So using this kind of metric isn't necessarily going to be in agreement with the greatest reduction in the trace of the analysis error covariances. But this is possibly not giving you a full picture of the value of the observations. So in the case when R is only known approximately, which it generally is because we're still at the early stages of really trying to estimate R, then there's a potential for, if you're going to increase the density of the observations, that assimilating a much larger number of observations could have a detrimental effect on the analysis. So for example, overfitting and overconfidence, and the analysis could end up being worse than the prior. So this risk can be reduced by overestimating the observation uncertainties, which has obvious implications for choosing the error variances. But in terms of choosing the length scales in R, it's a lot more subtle, and it depends on how the true R and the B matrix relate to each other. But I focused on the case when the observations are relatively more certain than the prior at small scales. So the case when we'd want to use that dense information in the observations. And in that case, it seems that it's safer to underestimate the length scales in R, which is the same as overestimating the observation uncertainty at the small scales. So I will finish there, but thank you very much.